Right now, thousands of pounds of completely invisible force are actively trying to tear apart the building you are sitting in.
Oh, absolutely. It's happening constantly.
Right, like the structural beams above you are fighting this endless battle against gravity, and the pressurized pipes in the walls are fighting to contain volatile fluids.
Even the chair you're sitting on is actively resisting your body weight right now.
Exactly. We live
Yeah.
our entire lives inside these engineered structures, and we just, trust them implicitly.
Yeah, we rarely think about it because the battle is entirely invisible to us.
But if you strip away the drywall and the concrete, like what is actually happening at a molecular level when the physical world pushes and pulls on solid metal?
Well, the atomic structure of a steel beam is basically holding off catastrophic failure every single second of the day. And we only really notice it on the rare occasion that the physical forces win and the material just snaps.
Which is exactly why we are pulling back the curtain on that microscopic war zone today. Welcome to this deep dive.
I'm really excited for this one.
Me too. You and I are going to explore a highly detailed applied physics and mathematics training module. It was originally designed for first period instrument technicians by the Northern Alberta Institute of Technology, NAIT, and the Southern Alberta Institute of Technology, or SII.
It is a seriously rigorous foundational text. I mean, it strips away all those casual assumptions we make about solid objects and just mathematically deconstructs the precise mechanics of elasticity.
Yeah, so our mission for this deep dive is to explore the invisible physics of elasticity. We're going to figure out exactly how solid materials bend, stretch, and ultimately why they break.
Because that applies to practically everything around us.
Right. Whether you are a technician calibrating high pressure control valves in a refinery or you just want to understand why the suspension bridge you drive over doesn't, collapse into the river.
Yeah, understanding the atomic response to intense forces is really the key to decoding our modern physical world.
But we have to start by defining the invisible forces themselves. Okay, let's unpack this.
So, the text immediately establishes two foundational concepts that people, well, they often blur them together in everyday conversation.
Stress and strain.
Exactly. Stress and strain. In physics and metallurgy, these are distinct, highly specific terms. Before we can break a material, we have to measure what is actually acting upon it.
Right, so I want to look at stress first, which is represented by the Greek letter sigma. And we aren't talking about like emotional stress here.
No, no. Not your deadline at work.
Right, we are talking about a measurable mechanical force. Actually, I have an analogy for this.
Oh, let's hear it.
Okay, so stress is like the invisible internal pressure you experience, like having way too much to do at work, while strain is the physical, visible deformation that results from it, like the wrinkles on your forehead.
Okay, I mean, that's surprisingly accurate. If we look at the internal mechanics of a metal, it's like visualizing the atomic bonds as billions of microscopic bungee cords.
Oh, I like that.
Yeah, and stress is the measurement of how much pulling force is being distributed across those specific bonds. The module defines it mathematically as the stretching force divided
Wow.
by the cross-sectional area of the material. Force over area.
Force over area.
Right. And if you look closely at that formula, you notice that stress shares the exact same units as pressure.
Wait, really? Like fluid pressure?
Exactly like fluid pressure. We typically reserve the word pressure for fluids or gases, like water pressure inside a pipe pushing outward.
Right.
Well, stress is simply the solid state equivalent of that. It's how an applied force distributes itself across the internal cross-section of a solid.
And it's measured in pascals or like megapascals, gigapascals, or pounds per square inch, right?
Yep, size, spot on.
So pressure is for fluids and stress is for solids. That clarifies the mechanics beautifully. And then we have strain, which is represented by the Greek letter epsilon.
Right.
So if stress is the invisible internal force, strain is the physical, measurable deformation that results from it.
Precisely. Strain is the actual elongation or compression per unit length. It's the change in length divided by the original length of the material.
Change over original.
Yeah. And mathematically, this creates a really unique situation. Strain has no units at all.
Wait, no units because it's a ratio.
Exactly. Because it's a ratio. If a 1 meter steel rod stretches by 1 millimeter, you are dividing a length by a length. The units, the meters, they just cancel out.
Oh, wow. So strain isn't a measurement of distance at all. It's just a fractional change, like a percentage of deformation.
Yep. The force causes the deformation, the stress causes the strain.
Yeah.
But the text doesn't just treat force as a single monolithic concept. It outlines 5 distinct types of load forces that materials endure out in the real world.
Okay, so what are the 5 types?
Well, we have tension, which is pulling apart. Compression, which is squashing together. Torsion, which is twisting. Shear, where forces act close together but not directly opposing. And bending, which is deflecting or sagging.
Okay, instead of just listing them out, let's look at how they all operate simultaneously in an actual industrial environment.
Oh, good idea.
Imagine you've got a massive, high-pressure control valve bolted into a pipeline. The heavy steel bolts clamping the valve flanges together, those are under tension, right? Directly opposing forces are trying to stretch those bolts and pull them apart.
Meanwhile, the steel gasket sitting right between those two flanges is experiencing compression. It's trapped, and two opposing forces are actively trying to squash it flat.
Right, and then you have the fluid rushing through the pipeline itself. As the high-pressure liquid drags against the internal walls of the pipe, it creates shear stress.
Yeah, the forces are acting close together, sliding parallel past one another, trying to basically tear the surface of the metal away. It's much like the two bypassing blades of a pair of scissors cutting paper.
Okay, so tension, compression, shear. And when the automated actuator on top of that valve kicks in to close it, that applies torsion to the valve stem.
Exactly. A turning force is twisting the solid metal shaft to shut off the flow.
And finally, think about the long span of heavy piping leading up to that valve. The sheer weight of the pipe suspended between two support brackets causes bending.
Because gravity is applying a perpendicular turning force, basically trying to make the solid steel sag right in the middle.
Tension, compression, shear, torsion, and bending. Every engineered structure around us is constantly fighting off some combination of these 5 loads.
But the metal doesn't just instantly snap when these loads are applied, it flexes.
Right, the atomic bonds stretch to accommodate the stress.
Exactly. Which brings us to a fundamental principle of physics outlined in the module, and that is Hooke's law.
Okay, so Hooke's law dictates that for most solid materials, as the applied force increases from 0, the stress and the strain increase proportionally.
Yes. So if you double the pulling force on a steel rod, the atomic bonds stretch twice as far. The relationship is perfectly linear, well, up to a certain point anyway.
And the constant of that proportionality, like the exact mathematical ratio between the stress applied and the resulting strain, that is called Young's modulus of elasticity, represented by a capital E.
You calculate it simply by dividing the stress by the strain.
So I was reading through the module's data tables, and Young's modulus acts almost like a mathematical fingerprint for every pure metal.
It really does. It depends only on the material's composition. It doesn't matter if you have a microscopic wire or a massive architectural I-beam.
If they're made of the exact same material, they share the exact same modulus.
Right, because you are measuring the shape of the object. You are measuring the inherent stiffness of the metallic bonds themselves. The atomic lattice of each element resists pulling in its own unique way.
Looking at the chart here, aluminum has a fairly low Young's modulus at 68.9 gigapascals.
Yeah, so it deforms relatively easily.
Right. Brass and iron are stiffer, both sitting at 89.6 gigapascals. Copper comes in at 117 gigapascals, and steel tops the list at a massive 207 gigapascals.
Those numbers are incredibly useful. The module actually provides an excellent engineering application to show how you can use these fingerprints to identify unknown materials out in the field.
Oh yeah, let's walk through that math. It's a great example. So say you are working with a mysterious metal wire suspended in a shaft. You know it's exactly 128 meters long.
Right.
The text establishes a scenario where a 380 Newton force, which is roughly the weight of a heavy piece of machinery, is hung from the wire. Based on the wire's specific cross-sectional area, that 380 Newton force generates a specific amount of internal stress.
Then you measure the deformation.
Yeah.
Under that load, the entire 120-meter wire stretches by a mere 0.10 meters, just 10 centimeters.
Okay.
You calculate the strain by dividing that 0.10 meters of stretch by the original 120 meters.
And when you divide the calculated stress by that minute fractional strain, the formula yields a Young's modulus of approximately 120 gigapascals.
Which is the magic number.
Right. Looking back at the atomic fingerprints we just discussed, aluminum is 68.9, iron is 89.6, and copper is 117.
So we can confidently deduce that this mysterious wire is made of copper.
That's amazing. The math allows the internal atomic structure to basically reveal its identity without us ever having to run a chemical analysis.
The elegance of that formula is undeniable. But, raises a critical question regarding the source material.
Which is?
How did the industry establish that steel has a Young's modulus of 207 gigapascals in the first place?
Yeah.
You can't calculate the absolute limits of an atomic lattice with theoretical math alone. You have to force the material to fail.
Ah, you have to break it on purpose.
You have to break it.
The module describes the ASTM standard .505 tensile test. When I look at the schematics of a stationary tensile machine, it literally resembles a highly calibrated medieval stretching rack.
It really does.
It uses these heavy hydraulic grips to clamp onto a standardized, specifically machined cylinder of metal, and then it just relentlessly pulls the specimen apart. But I have to ask, are we just ripping metal apart for fun, or is there a bigger purpose here?
If we connect this to the bigger picture, this test generates the stress-strain diagram. It's not just destruction.
Right.
By recording every micromillimeter of stretch against the applied hydraulic force, designers and quality managers can predict exactly how that specific batch of steel will behave when it's manufactured into crucial applications like control valves, flanges, and piping.
To measure that stretch with absolute precision, the technician actually uses a center punch to mark two tiny indentations on the test piece exactly 50 millimeters apart.
Yep, that's the gauge section.
Right, the gauge section. And as the hydraulic machine begins to pull, sensors constantly track the expanding distance between those two microscopic marks.
And this is where the physics become incredibly dynamic. The module charts the entire life cycle of a piece of steel as it undergoes this test.
Here's where it gets really interesting.
Yeah, we can trace its journey on the stress-strain diagram, starting right from zero force. Let's trace it.
Okay, machine powers up and begins pulling. At first, we are in the elastic deformation region. The steel acts like a perfectly stiff spring.
Right. The hydraulic force increases up to 276 megapascals, which is roughly 40,000 psi of internal stress.
The steel is stretching, but the atomic bonds haven't slipped yet.
Exactly. If you were to shut down the hydraulic pumps right then and remove the load, the steel would perfectly recover its original 50-millimeter gauge length.
Like a rubber band snapping back.
Exactly like a rubber band. But the machine doesn't stop. It continues to increase the pulling force. And at 297 megapascals, or 43,000 psi, we hit a critical threshold, the yield point.
The yield point. This is the physical point of no return, right? We transition from elastic deformation into plastic deformation.
Yes. The pulling force has officially overwhelmed the atomic bonds. The crystalline planes of the iron atoms actually begin to slide past one another.
The internal structure is slipping.
Right. If you stop the test now, the steel will never go back to its original shape. It is permanently structurally altered.
The metal has yielded, but it hasn't completely failed yet. The machine keeps applying more and more force, driving the stress higher as the steel continues to plastically deform.
And finally, the curve peaks at the ultimate tensile strength, or UTS.
Okay.
For this specific steel, the UTS hits at 414 megapascals, or 60,000 psi. This is the absolute greatest stress the steel can withstand.
And shortly after that peak, we hit the fracture point. The specimen completely failed and breaks apart at 317 megapascals with a strain of 0.250.
Right.
But wait a second, I noticed a glaring discrepancy here. The ultimate tensile strength, the absolute peak stress the metal survived, was 414 megapascals.
Yeah.
But it breaks at the actual fracture point at only 317 megapascals. Why does it take less force to finally snap the metal than it did to stretch it? The physics of that feel completely backward.
I know, it seems counterintuitive until you look closely at the physical mechanism of the metal right before it breaks.
Huh.
It is a phenomenon called necking.
Necking, like what are the physical mechanics of what is happening to the cylinder of metal there?
Okay, so when the steel surpasses its ultimate tensile strength, it stops stretching evenly across that 50-millimeter gauge length.
Oh, I see.
The extreme plastic deformation localizes into one specific spot. The material begins to rapidly thin out, forming a narrow neck right in the center of the specimen.
So the cross-sectional area drops dramatically. And if we go back to our formula, stress equals force divided by area. If the area suddenly shrinks by half, the physical mass available to carry the load is just gone.
Exactly. Because the neck is so thin, it literally can't carry the same load anymore. It required significantly less overall force from the machine to continue tearing those remaining atomic bonds apart.
Wow.
So the required load drops off sharply right before the violent fracture. That localized thinning is the metal's ultimate downfall.
Okay, so what does this all mean? Knowing exactly how and when steel fails allows us to engineer safety, right?
Yes, absolutely. We aren't testing metals in a lab just to catalog their failure points. We're testing them so designers can stay incredibly far away from those points in practice.
Which introduces the engineering concept of the factor of safety.
Right. No competent engineer designs a structural beam to withstand exactly the ultimate tensile strength. They design using what is called the safe working stress, or the allowable stress,
You calculate the allowable stress, you don't even look at the ultimate breaking point. You look at the yield point, the moment of permanent deformation.
which for our steel example was 297 megapascals.
Right. You take that yield strength and divide it by a strict factor of safety. So if a pipeline requires a safety factor of 3, you divide 297 by 3.
Leaving you with a maximum allowable stress of 99 megapascals. By enforcing that limit, engineers ensure the material never even reaches permanent deformation. It operates exclusively in its elastic range.
But the module goes further, doesn't it? It emphasizes that we're not simply stuck with the inherent yield point or UTS of a metal. Metallurgy allows us to actively manipulate solid steel to drastically alter its mechanical properties.
Yes, and the text outlines 4 specific methods for doing this.
The first method is heat treatment.
Right. By subjecting the solid metal to highly controlled cycles of extreme heating and rapid cooling, processes like quenching or tempering, you can actively manipulate the crystalline lattice.
So depending on the exact thermal cycle, you can significantly increase or decrease both the yield strength and the UTS.
Exactly. The second factor is environmental temperature. The text highlights a really interesting nuance here.
Yeah, as the temperature rises, say, inside a high-temperature steam boiler, the steel becomes more ductile, and its ultimate tensile strength and yield strength actually decrease.
The heat energy makes it easier for the atomic planes to slide. But cold temperatures operate differently. The text explicitly notes that freezing temperatures do not lower the ultimate tensile strength or yield strength.
Wait, really? Cold temperatures don't weaken the tensile strength.
Nope. Extreme cold can certainly decrease a metal's impact toughness, making it more brittle if you strike it violently. But if you're strictly applying a slow, steady tensile pull, the cold actually locks the crystal lattice in place.
So it requires just as much, if not slightly more, sheer force to pull those atomic bonds apart in freezing conditions.
Exactly.
Okay, the third method for manipulating metal is through alloying elements. You introduce foreign atoms into the pure iron base. The module points to carbon as the critical alloying element for strengthening steel.
The mechanism behind this is just fascinating. Iron atoms naturally arrange themselves into a neat, uniform grid. But when you introduce carbon atoms, which are significantly smaller, they wedge themselves into the tiny interstitial spaces between the iron atoms.
Like microscopic roadblocks.
Exactly like roadblocks. When intense stress tries to force the planes of iron atoms to slide past one another, which is what happens at the yield point, those carbon atoms physically block the movement.
The more carbon roadblocks you add, the more force it takes to deform the steel.
Right. And the fourth and final method discussed is cold working.
Cold working. This is the intentional plastic deformation of a metal at room temperature to form it into a desired shape, like rolling a thick steel billet into a thin sheet or drawing a thick rod through a die to create wire.
And the physics of cold working lead us to perhaps the most profound concept in the entire module.
Oh, absolutely.
When you intentionally push a metal past its yield point at room temperature, you are forcing the internal crystal structure to slip. But as those atomic planes slide, they start crashing into each other. They create these tangles of microscopic defects called dislocations.
The more you deform the metal, the more tangled and locked up the internal structure becomes. And because it's tangled, it becomes vastly more difficult to deform it any further.
Exactly. According to the source material, intentionally subjecting a metal to severe plastic deformation, basically pushing it past its elastic limit so it is permanently deformed, actually increases its ultimate tensile strength and its yield point for future use.
It's so wild because we spend so much time in engineering trying to avoid the yield point. We calculate massive factors of safety to ensure we never permanently deform our materials because we equate permanent deformation with damage.
Right, with failure. Yet, in metallurgy, trauma to the internal structure is exactly what hardens it, forcing the material to stretch beyond its natural limits, tangling its internal architecture, physically makes the steel stronger and more resilient to future stress than it was in its pure, unaltered state.
It fundamentally changes how you view the concept of damage.
It really leaves you with a final thought to mull over. Are there other complex systems in our world, perhaps architectural, biological, or even societal, that fundamentally require permanent deformation and extreme stress in order to achieve their ultimate strength?
The idea that being pushed relentlessly past your elastic limit might be the precise mechanism required to maximize your strength is just an incredible thought to end on. We have traced the invisible forces of stress and strain down to the atomic level, watched steel stretch and break on the tensile machine, and uncovered how manipulating those atomic structures builds the physical world around us. Thank you for joining us on this deep dive into the hidden mechanics of the materials we trust our lives to every day.